All right, what if I told you there was a way to solve some of the trickiest energy puzzles in chemistry using just, basic addition and subtraction? Sounds too good to be true, right? Well, today we're diving into that exact secret weapon. It's called Hess's Law.
Okay, so let's start with a puzzle. Imagine you're a chemist, and you've got this super important reaction on your hands, maybe for a new type of battery. But there's a catch, a really big one. You can't actually run it in the lab to measure its energy change. So, how could that even happen? Why would a reaction be impossible to measure?
Well, the surprising truth is, a lot of really fundamental reactions in chemistry are, they're pretty much impossible to measure directly in a lab setting. Think about it. Some reactions, like the ones that create minerals deep inside the Earth's crust, they take thousands of years. You can't just sit around waiting for that. Or on the other end of the spectrum, some are just, bam, super explosive, way too dangerous to handle. And then there are the messy ones, where you end up with this chaotic soup of unwanted side products, making it totally impossible to isolate the one energy change you actually care about. So, what do? How do scientists crack this problem? This is where the magic happens. They use this incredibly clever workaround, almost like a master key for chemical energy. And that key is Hess's Law. This is exactly how we get to unlock the secrets of all those impossible reactions. So here's the core idea, and it's actually pretty simple. The total energy change for a reaction, which we call enthalpy in chemistry, is always the same no matter how you get from start to finish. It doesn't care about the journey. This is what we call a state function. All that matters are the starting and ending points. The path you take in between, totally irrelevant. A great way to think about it is like planning a road trip. Let's say you're going from New York to Los Angeles. Your change in location, the distance between the two cities, is fixed, right? It doesn't matter if you take a direct flight or if you decide to drive the scenic route through a dozen states. The start and end points are the same. Well, Hess's Law is just that same powerful logic, but applied to chemical reactions. And what's so cool, so elegant about this whole thing is that it lets us treat chemical equations like they're a game. Seriously, we can flip them, scale them, and combine them just like puzzle pieces or simple algebra problems. All we have to do is follow two really, really straightforward rules. So what are the rules to this game? Super simple. Rule number 1, if you flip a reaction around, make the products into reactants and vice versa, you just flip the sign of its energy change. Easy. Rule number 2, if you need to multiply a reaction by some number, say you need to double it, you just multiply the energy change by that same number. That's it. That's the whole playbook. Okay, enough with the theory, right? Let's get our hands dirty and actually put these rules into practice. We're going to solve a real problem now, exactly the kind of thing you'd see on a tough chemistry test. Okay, here we go. Here is our challenge. The reaction you see at the top, that's our target. That's the final puzzle we're trying to solve. And down below, those are our puzzle pieces, a couple of known reactions with their energy changes already figured out for us. Our mission, should we choose to accept it, is to manipulate these pieces until they add up to our target reaction. Let's walk through the logic here, step by step. First, let's look at our target. We need that iron oxide, Fe2O3, on the left side as a reactant. But if you look at our first puzzle piece, reaction number 1, it's on the right side as a product. No problem. We just use rule number 1 and flip the entire reaction. And when we do that, we have to flip the sign of its delta H, so negative 822 becomes a positive 822. Got it? Okay. Next up, we need 3 solid carbons. Our second piece has carbon on the correct side, which is great, but it only has 1. So we use rule number 2. We just multiply that entire reaction by 3. And of course, that means we also have to multiply its energy change by 3. Now we've got our pieces arranged just right. So now for the final step, we just add up our new manipulated energy values. We take our positive 822 and add the negative 330. And what do we get? Boom! Positive 492 kilojoules per mole. And just like that, without ever setting foot in a lab, we've calculated the exact energy for our target reaction. That, right there, is the power of Hess's Law. All right, you feeling confident? Ready for level 2? Let's crank up the difficulty a little bit and tackle a puzzle with 3 pieces this time. This is really going to show you just how powerful and flexible this method is. So this time, our big goal is to figure out the enthalpy of combustion for benzene. Basically, how much energy is released when it burns. And as you can see, we've got 3 different reactions to work with. It might look more complicated, but don't worry. The strategy is exactly the same. Find what you need in your pieces, and then flip them or scale them to match your target.
Okay, let's run through the plan. First, we need benzene, C6H6, as a reactant on the left. Equation 1 has it as a product, so we flip it. And that means its delta H becomes negative 48.5. Check. Next, we need 6 carbon dioxides on the product side. Equation 2 gives us 1, so we multiply that whole thing by 6, including its delta H. Check. And finally, we need 3 liquid waters on the right. Equation 3 has 1, so we just multiply it and its energy by 3. Check. Now all our pieces are in place, so let's add it all up.
And when you do the math, you get a massive negative 3,267.5 kilojoules per mole. Whoa, that huge negative number tells us that this reaction releases a ton of energy. It's super exothermic, which, makes perfect sense because we're talking about burning something. See? Even a 3-piece puzzle is totally manageable once you know the rules. So at this point, we've seen how to use Hess's law. It's a fantastic shortcut. But the really deep question is, why does it work? I mean, it kind of feels like a magic trick, doesn't it? But it's not magic at all. It's actually built on one of the most fundamental rock-solid laws in all of physics.
And it all comes down to this one beautiful, profound idea. Energy can't be created, and it can't be destroyed. It can only be transformed from one form to another. You've heard this before. It's the law of conservation of energy. And this is the solid bedrock that Hess's law is built on.
And here's where it all clicks. Hess's law isn't some random trick that just happens to work for chemistry problems. No way. It's a direct consequence of the first law of thermodynamics. Because energy can't just appear or disappear, the total energy gap between your starting chemicals and your final products is fixed. It's a constant. It absolutely does not matter what kind of crazy, multi-step, winding path you take to get from A to B, the overall energy change has to be the same. So let's zoom out for a second. This whole idea, this method of taking a big, messy, maybe even impossible-looking problem and breaking it down into smaller, simpler, measurable pieces, that's an incredibly powerful tool, right? It's the key to solving these energy puzzles in chemistry. But it makes you wonder, where else can we use that same thinking? What other complex systems in our lives could we understand better just by breaking them down into simpler parts?